Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to work on an example where you have to deal with a couple of probability distributions I'm sure you have seen before. The probability distributions that I'm talking about are the exponential and the gamma distributions. Let's begin. So that's the problem I would like to solve with you in this video. So we have an exponential distribution. Note that we are not given its parameter. Remember that the parameter of a beta, of an exponential distribution is beta, right? But we don't have beta. But what we know is that the probability that the random variable is greater than 2 is roughly 8%. Okay? And using that fact, somehow we have to come up with the expected value of y and with the probability that y is less than or equal to 1.7. Okay? Okay. So there are different ways of going about this. Okay? I'm going to suggest an approach that I think it's fun and useful. So how about we first try and find the CDF, the cumulative distribution function of a generic exponential distribution with parameter beta. Okay? Okay? Let's try and do that. See how that works for us. So let's see. So let y have an exponential distribution with parameters, with parameter beta. Okay, so it's just a generic random variable. Okay, so with an exponential distribution. So we know, right, that the PDF, the probability density function for that guy, let me use f of y. For the PDF, it's going to look something like this, right? It's going to be just 1 over beta times e to the negative y divided by beta, and that rule applies for y's that are positive, and we know that f of y is going to be 0 otherwise, right? Oops, sorry, not what I want. Otherwise. There. Okay. So now what I said is let's find the CDF. That might be useful, and you'll see in a second that it's going to be useful with this problem. So we know that the CDF, we use the notation uppercase F for this guy. Uppercase F, let me be very specific that we are referring to the random variable y. So anyway, the definition of the CDF, cumulative distribution function, is the probability that the random variable y is less than or equal to some number, right? Okay. So now in this particular case, right, if we apply that definition, right? The part that is going to matter, right, is this region for positive real numbers, right? So it's easy to find what's going to be the CDF when y is less than or equal to 0, just by the definition. What we're going to have is that the CDF there will be 0, right? Okay. The case that is important is going to be for positive y's, and note that if we have the probability that y is greater than 2, right? Well, we could express that in terms of the probability of the event that defines the CDF. This is going to be the same as 1 minus the probability that y is less than or equal to 2. Okay, so this probability could be re-expressed in terms of the CDF. So it's going to be useful. Here we go. So case number 2. Case number 2 for positive y. Okay, so let me again borrow the definition. So in that case, it's just going to be the integral from negative infinity to y of the PDF, right? Okay, now that's going to be just the integral from negative infinity negative infinity to 0 of 0 dt plus the integral from 0 to y of now, right, what we have here is the expression of a generic exponential with parameter beta. Okay, and let me change variables here. That's better. Okay, so now this is going to be 0 clearly. Now this one here is the only one that we have to be concerned about. Okay, so that's easy, right? We know that if we took the derivative of e to the negative t divided by beta, the derivative of e to the negative t divided by beta would be negative 1 over beta e to the negative t divided by beta, right? So what I'm going to be doing here is just multiplying by a1, negative 1 times negative 1, that's just a1, but then, as I said, we can clearly see that the integral that we want is just e to the negative t divided by beta, and we are going to be evaluating at 0 and y. Okay, so that is just going to be minus e to the negative y divided by beta minus e to the 0 power, that's just 1, right? So in the end, what we have is that our CDF will be just 1 minus e to the negative y divided by beta, right? CDF of the random variable y evaluated at lowercase y is just 1 minus e to the negative y divided by beta if y is positive. So that is going to be useful. Okay, you'll see. Let's go back to the original problem. Okay, so we have that the probability of y is greater, the probability of y being greater than 2 is 0.0821. Okay, so back to our problem. So we have that the probability that our random variable y is greater than 2 is roughly 8%, exactly 0.0821, right? But as I said before, note that we could rewrite the left-hand side, right? This is the same as 1 minus the probability that y is less than or equal to 2. Agreed? So we have that 1 minus the probability that y is less than or equal to 2 is the same as 0.0821, right? Furthermore, this guy here, 2, is a positive y. So from what we did before, we know that the CDF evaluated at some positive y is going to be 1 minus e to the negative number at which in this case y is positive, right? So let me call it k. The CDF of y evaluated at k is 1 minus e to the negative k divided by beta, right, for positive k's. So 2 is positive, right? So from what we did, what we have is this, right? This is 1 minus the CDF evaluated at 2, right? So what we have is 1 minus e to the negative 2 divided by beta. Right? So what we have is e, right? 1 minus 1, they cancel out. We have e. Let me copy paste this guy, e to the negative 2 divided by beta. It's going to be 0.0821. Right, now what we have to do is just apply natural log on both sides. So we have negative 2 divided by beta, natural log of 0.0821. We solve for beta, and then in the end, right, what we have is negative 2 divided by this guy, natural log of 0.0821 is our parameter of interest, beta. Okay, let's find it using R. First, I want you to see something. What we want is -2 divided by natural log. Okay, so if you want log, natural log, and you're using R, I want you to see this. See that the default base is E, right? So even when you're just typing log, this is not log base 10, right? This is the default here in R. When you do this log, what we mean is natural log. Okay, so in this case we want 0.08 to 1. So beta is roughly 0.8. Okay, beta is exactly that guy, and roughly 0.8. Okay, are we good? So now we have our parameter of interest. Okay, so now that we have the parameter of interest, we are going to be able to find the expected value. We have a couple of ways, right? Maybe some of you remember that the expected value of an exponential is beta. So if that's the case, we already have the answer, right? That the expected value for an exponential with parameter beta is just 0.8000585, right? Okay, now let's try and do it in a different way. Okay, we already know the answer, so let's see. So another way is, remember the definition of expected value for a continuous random variable is just the integral from -infinity to infinity of y f of y dy, right? Okay, so as we know, the only part that is going to matter for that calculation is going to be the region where the PDF is non-zero. Okay, the support. So we have y times the PDF, and the PDF of an exponential we already know is 1 over beta times e to the -y divided by beta, right? Okay, but now we know that this guy is this, right? So let me try and find it. Let me write down the generic expression for a beta. Okay, well, the generic expression for an exponential using beta instead of the actual value of beta. Okay, makes sense? Okay, so now the integral that we want is the integral from 0 to infinity of 1 over beta of y e to the -y divided by beta times dy. Okay, very good. Now one way of finding that integral, take a look at it and then you'll go, oh, Okay, so we could do it by parts, right? That would be one way using those calc techniques. So you could do integration by parts, and you could find that integral, right? Now, another way would be using a trick that we have used before, right, in other videos, and one that we're going to be using again frequently in this course. In Bayesian statistics we do this a lot. Okay, we're going to try and see if we can find a function, a probability density function that looks like this, and then we're going to try and complete that. So if this happens to be the support of legit PDF, we know that if you integrate a PDF over the entire support, then you have a 1. Okay. So what I want you to remember is a probability distribution that I'm sure you saw when you took sta313. Okay, the gamma distribution. We know that that guy has two parameters, alpha and beta. Let me remind you about the expression of the PDF of gamma with those parameters, right? A gamma with parameters alpha and beta, the PDF. Let me use X for that guy. It's going to look something like this, right? 1 over beta to the alpha power times the gamma function evaluated at alpha and then we have y to the power alpha minus 1 and e to the power negative y divided by beta, and the support is going to be y must be positive, and it's 0 otherwise. Okay, well, I'm using X, right? Let me be consistent. There. So 0 otherwise. Okay. Okay. So as you can see, this guy here, right, up to that constant, looks like this. So let's try and complete. Let's try and do something at the right constant so we can have a complete gamma, right, the PDF of a gamma, and then since the support is the right one, is, you know, positive real numbers, then whatever we have inside here is just going to be 1. Okay, if we have inside that integral from 0 to infinity the expression of gamma with parameters alpha and beta. Okay, so here we go. So this is the same, y is the same as oh, come on, what's that? Okay, that's better. Won't do it. So I just want to have power 2 minus 1. That's the same as y, right? So note that then this guy, the one that we need, is 1 over beta. It's already there. Alpha is going to be 2, gamma evaluated at 2. Okay, so let me do that. Divide by beta. We know that beta is roughly 0.8 to the power alpha, in this case 2, and gamma function evaluated at 2, right? But since we're dividing by that quantity, and again beta is just a constant and gamma at 2, the gamma function evaluated at 2 is just a constant as well, so we just have to multiply by that same constant outside that integral, and then we're not doing anything wrong, right? We're just multiplying by a1. But by doing that, now since we are integrating a gamma with parameters alpha equals 2 and beta equals 0.80025, right? Then this guy here, the integral is just 1, right? Okay, so what we have here is beta squared divided by beta. That's just beta. And we know that the gamma function evaluated at a positive integer is just if the positive integer is n, then gamma evaluated at n is n minus 1 factorial. In this particular case, the gamma function evaluated at 2 is just 1 factorial, which is just 1. So what we have shown is that the expected value of an exponential is just beta. Okay? Okay, so we are done. So in this case, the exponential is just this guy, right? Oops, 0.80, this guy here. Okay. Okay. Now, let's see. Part B. We want to evaluate the probability that y is less than or equal to 1.7. Part B. Probability that the random variable is less than or equal to 1.7. 1.7. Oops. Note that that happens to be just the CDF of a random variable y evaluated at 1.7, right? So we know that the expression is this, right? If y is positive, the CDF evaluated at some point, lowercase y, is 1 minus e to the negative lowercase y divided by beta, right? Okay, so that's exactly what we have here. Y happens to be 1.7, beta happens to be 0.800, so on, right? So we can easily find it using R, right? So 1 minus e to the negative 1.7 divided by 0.8000585, right? Okay, that's it. Okay, let's summarize what we did. So, in this case, we were interested in solving a problem that had to do with an exponential distribution, a random variable that was exponentially distributed. Beta was not given, but we had this as our initial information. So what we realized is that we could relate that probability to the CDF. So what we did first is we found the expression for generic an expression for a generic random variable with exponential distribution and parameter beta. So we found this expression, right? We used it to obtain beta. Then since we wanted the expected value of an exponential random variable, right, we used the definition, and we actually obtained the general formula for the expected value of an exponential distribution. The expected value for an exponential distribution happens to be beta, right? And what we used along the way to find that was instead of doing that integral by parts, the one that we had to find to compute the expected value, what we did is we used a trick. We completed the integrand. We turned the this function here inside that integral into the PDF of a function we know is a legit probability density function, a gamma. Okay, so along the way we recalled that we have seen this guy before, okay, that family of distributions. Okay, and yeah, basically that was it, because part B was easy once we had the expression for the CDF of a generic exponential with parameter beta. Okay, so that was it. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.